So to identify G, or you have to identify which reaction is this. NaOH, if you take dilute, although I have not mentioned whether it is dilute or concentrated, but if you consider that NaOH is dilute, then no reaction is going to occur because there is no acidic hydrogen. These hydrogens are not acidic because if you abstract a hydrogen from here, the negative charge developed on carbon is not going to do resonance with C double bond O because they are not at alpha position. This hydrogen is not acidic. We discussed this when we studied Cannizzaro reaction. So this has to be a conc NaOH. You write it or not, you will consider it a conc NaOH. When you take it as a conc NaOH, the reaction that is going to occur is called Cannizzaro reaction. Good. So in Cannizzaro reaction is a disproportionation reaction. The substrate is going to be oxidized, the substrate is going to be reduced. So when aldehyde gets oxidized, it gets converted into carboxylic acid. So you just make that aldehyde group as carboxylic acid. Because I have not protonated it, so it will be in ionic form. It will be a carboxylate ion. Right? So there will be two products. So it should be G plus H. So one of them out of G plus H, G and H is this carboxylate ion, and the other one will be the reduced form of this aldehyde, which is alcohol. So one is G, one is H. Fine. The mechanism we have seen in great length when we studied Cannizzaro reaction. I hope you practice that. So I hope there will be no problem for you to identify that these will be the products of this reaction. So this conversion problem is done. Fine. Fine. So Wittig reaction is done. So we are moving towards the end of this chapter. There are few reactions left out. Let's quickly finish them off, and I hope we have studied those reactions already, so it will be quick. Very quickly we'll be finishing them off. Now we are moving towards a kind of reaction that is reduction of carbonyl compound. Now when we carry out reduction of carbonyl compound, suppose I have a carbonyl compound like this, then this can be reduced to alkane. This is one kind of reduction, that oxygen has been removed and hydrogen has been added. This can be reduced to an alcohol. So this carbonyl group can be reduced to alkane, this can be reduced to alcohol. Fine. So both are reduction because both involves addition of hydrogen or removal of oxygen. So both are reduction reaction. So quickly first we will be looking at this kind of reduction where carbonyl compound will be reduced to alkane, and next very quickly we'll see this kind of reduction where carbonyl compound will be reduced to alcohol. So let's start with the first kind where carbonyl compound will be reduced to alkane. So this first kind reduction, this kind of reduction I have taught you when I taught you alkanes, because carbonyl compound is being reduced as alkane. So I taught you there as this method of preparation of alkane. Now we are going to study this as reaction of carbonyl compound, but perhaps we didn't see the mechanism in detail. So I told you the reaction and I helped you learn how to write the product of the reaction. But here's a time when we will be studying the mechanism of this reaction. The name of the reaction, we call it as Wolfe-Kitchener reduction. Now what happens in this is, let's start with benzaldehyde. You take benzaldehyde, you take hydrazine, NH2, NH2, and you take a base along with this. When this you take, then this oxygen is removed and two hydrogens are added. So this turns into toluene. Let's see how this happens. The first step would be, remember when we started studying the reactions of carbonyl compound, then we studied a reaction where ammonia derivative was added. This addition elimination. So if you take any carbonyl compound, then what happens is this two hydrogen and this oxygen comes out in form of water. We studied this, remember? And this carbon and this nitrogen forms a double bond, and this Z remains as it is. So we have studied this reaction before. So what will happen is this Z here is NH2. So this nitrogen will form a double bond with this carbon and will have this NH2 intact. So in the first step of the reaction, this nitrogen, this hydrazine NH2 will get added on this carbon, and after elimination you are going to have this. 2 hydrogen from here and oxygen from here is going to come out in the form of water. So this is what you're going to get once you do addition elimination, mechanism of which we have seen when we studied this addition elimination reaction, perhaps the third reaction in this chapter. For the third reaction for reactions of aldehydes and ketones. Fine, so you have this. Now the base will come into picture. Base comes, what does base do? Base abstracts hydrogen. Which kind of hydrogen? Acidic hydrogen. Where is acidic hydrogen? This hydrogen is not acidic hydrogen. We understand it. We discussed it when we studied Cannizzaro reaction. This hydrogen is acidic hydrogen. Reason being, when you remove this hydrogen, the negative charge appears on nitrogen. Nitrogen is stable. Negative charge on nitrogen is stable because nitrogen has high electronegativity value. So this hydrogen from the nitrogen is going to be abstracted. So let's do it. This is what you're going to have. Now this negative charge obviously is in conjugation with this double bond, so it can't help but do resonance. Did I draw the resonating structure properly? Yes, I did. Were you able to draw it properly? Alright, so this negative charge is going to come here. So this negative charge is going to be on both the atoms, this nitrogen and this carbon. And as we have discussed before, the reaction occurs from the site that is less stable. So although most of the charge density will be with this nitrogen, because this RS is more stable, this RS is less stable, but for the reaction, the site is this carbon. Right? So when we have to proceed ahead for the reaction, we will start with this resonating structure. Now look, this base abstracted hydrogen from here came out as water, right? Because negative charge was coming on nitrogen. Now after resonance, when negative charge went till carbon, that base have to return that hydrogen which it took from this nitrogen with all due respect. Why? Because negative charge on carbon is not stable. It has to go. So that hydrogen has to be returned back. Alright. So this high carbon now has this hydrogen, and this again becomes OH minus. We'll again go for the reaction. And this part remain as it is. Fine. Now the base has been regenerated and there are other molecules of hydroxide present in the system as well. They'll come again. When they comes this time, then again they'll search for an acidic hydrogen. Now this is the hydrogen that is acidic because this is attached to nitrogen, and that to sp2 hybridized nitrogen. So this is going to be abstracted. When this is going to be abstracted, what do we have? We have this. This time there will be no resonance because the negative charge is on the pi bond itself. It is not in conjugation with the pi bond. So if you don't do anything, the reaction is going to stop here. But along with this, if we heat the system a little bit, or if we shake vigorously the system or the test tube in which the reaction is occurring, then what is going to happen is a very good leaving group is going to come out. Look, leaving groups are those which have independent existence, and this N triple bond N is a nitrogen gas, and this is very, very stable. The bond energy of this N triple bond N is twice as much as C double bond O. When we make so much hue and cry for this C double bond O formation, then we have to do everything to get this C double bond N triple bond N to be formed.